Good morning, students. Today we are going to discuss about losses in transformer. Okay. So in last class we discussed transformer construction, working, and applications. Right? Okay, students. Therefore, today we are going to see about losses in transformer. Okay. Now, losses in transformer. See this. In any electrical machine, loss can be defined as the difference between input power and output power. So the loss is nothing but difference between input power and to the output power. Okay, right. An electrical transformer is an static device, hence mechanical losses are absent in it. Mechanical losses does not takes place, right? Okay, and a transformer only consists of electrical losses. Which losses? Electrical losses. Okay, right. All these losses in the transformer are dissipated in the form of heat. So all the losses, 99% losses dissipated in the form of heat from the transformer. Okay, students, right? So that is electrical losses. Which losses? Electrical losses, right? Okay, and then yes, come to the types of losses in the transformer. Okay, types of losses. There are, yes, four types. Major types are four types. So based on the material, again the losses classified into two types. Okay, now come to the major, yes, losses. Four types of losses. The first one is iron or core losses. We called iron losses. Okay, right. The iron losses, because that the transformer made up of is iron, so based on that, iron losses classified into two types. One is hysteresis losses and eddy current losses. Okay, and now the second one is copper losses. Which losses? Copper losses. And third one is stray losses. Which losses? Stray losses. And the fourth one is dielectric losses. So the losses in transformer classified into four types. One is iron loss, and next second one is copper loss, and third one is stray loss, and the fourth one is dielectric losses. So these are the types of losses. Okay, but in our book only three losses given. Okay, students. Okay, first I'm going to explain that other losses, and then I'll explain book content. Okay, students, right? Okay, now first one is copper loss. Which one is copper loss? What is copper loss? See this. Copper loss is due to power wasted in the form of I square R, because power is equal to I square formula, no? That is I is the current through passing through the coil winding, and R is the internal resistance of the coil. Yes, therefore the square of current and the resistance. Okay, power losses takes place in transformer. Okay, right. Second point, it is clear that copper loss is proportional to the square of the current, and the currents depends on the load. The loss, copper loss, is directly proportional to square of the current, the same time amount of current passed to the winding. Okay, and hence the copper loss in transformer varies with the load. Hence it is also called as variable loss. Variable losses. See the work done here. Work cut the I square R. This is I square P is nothing but primary coil. The power loss in primary coil plus power loss in secondary coil. So yes, sum of the power loss primary and secondary is nothing but total power. That is total amount of work done. Okay, or power loss. Pri for primary coil and S for secondary coil. That is primary winding and secondary winding. Okay, students, because winding is nothing but coil, copper. Okay, right. And next is iron loss or core loss. See this. These losses occur in the core of the transformer and are generated due to the variations in the flux, due to the variation of flux in the core, and they depends upon the magnetic properties. They depends upon the magnetic properties of the material used for the construction of the core. Yes, because construction we discuss now. So based on the construction of the core, that means material used in transformer, based on the material used, copper loss or iron loss takes place. Okay, right. And hence these losses are also known as core losses or iron losses. It is denoted by Wi. See, this is the total loss. W is the cut, is nothing but total loss, and this is the what? Which loss? Iron loss. Okay, students, right. Next, eddy current loss. Eddy current loss. In the transformer, the leakage magnetic flux linked with the conducting parts like steel core or iron body of the transformer. In the transformer, the leakage magnetic flux linked with the conducting parts like steel core or iron body of the transformer, which will result in inducing EMF in those parts, causing small circulating current in them. Therefore, see that the leakage eddy current loss is denoted by WE, which is equal to S copper and this magnetic field square of the magnetic field in the F square. Yes, so this W is denoted by eddy current loss. Okay, and this current is called as eddy current. Due to these eddy currents, some energy will dissipated in the form of heat. So the eddy current also produced in the form of heat. Okay, right. Lamination of core material can be reduce the eddy current loss. So with the help of laminated sheets, we can reduce the loss. Which loss? Eddy current loss. We can minimize the eddy current loss with the help of laminated core. Okay, students, right? Okay, next, hysteresis loss. So the hysteresis loss is due to the repeated magnetization and demagnetization in the transformer core. Magnetization and demagnetization, because when the current flow to the coil, so the winding acts as a magnet. Yes, that is magnetization process. And after that, if you are reduce the current, the magnetic field is reduced. Due to that time, demagnetization process takes place. So the hysteresis loss only takes place due to magnetization and demagnetization in the core. Yes, so the energy is lost in each hysteresis loop. So this is the loop. Okay, hysteresis loop. Okay, students, We discussed in third lesson. Please remember, we discussed in third lesson. Okay, students? Right. And next, come to the book content. Yes, in book, first one is core loss or ion loss. Right, see this loss takes place in transformer core, and hysteresis loss and eddy current loss are known as core loss or ion loss. So hysteresis loss and eddy current loss are known as core loss. Right? Okay. When transformer core is magnetized and demagnetized repeatedly by the alternating voltage applied across primary coil, primary coil. At the same time, hysteresis takes place, due to which some energy is lost in the form of heat. So the core loss produced in the form of heat. Okay, right. And hysteresis loss is minimized by using steel of high silicon content. So please note it down. Hysteresis loss is minimized by using steel of high silicon content is in making transformer core. Okay, right? How to minimize the hysteresis loss? By using steel of high silicon. Okay, right. Next loss is copper loss. Which loss? Copper loss. See this? Transformer windings have electrical resistance. Transformer coil have electrical resistance because the copper has resistance now, that's why. When an electric current flows through them, some amount of energy is dissipated due to Joule's heating. When the current flow to the coil, around the coil, what will produce? Basically heat will be produced, no, that's why. So this energy loss is called as copper loss, which is minimized by using wires of larger diameter. If we use the large diameter, the heat loss will be reduced. Okay, students, that size of the wire is based on that amount of power generation. Okay, students, right. Third one is flux leakage. Which one? Flux leakage. Okay, now see the flux leakage. The flux leakage happens when the magnetic lines of primary coil are not completely linked with the secondary coil. The energy loss due to this flux leakage is minimized by winding coils one over the other. The energy loss due to this flux leakage minimized by using winding coils one over another. So we can reduce the leakage by this way. Okay, students, right? Okay. And this one illustration, this illustration is used to find out the power, electrical power. Okay, see this. For example, an electrical power of 2 megawatt is transmitted to place through transmission lines of total resistance is 40 ohm at two different voltages. One is lower voltage, that is 10 kilowatt, and other is higher, 100 kilovolt. Yes, how to calculate the power loss? How to calculate the power loss? For this illustration, there are two cases. That means there are two ways to find out the power loss for this illustration. Okay, now see the first case. The power is 2 megawatt. Yes, mega means 10 power 6, and the given resistance is 40 ohm, and that first two voltage is given. I am taking the first voltage 10 kilowatt. the power is equal to V into I, voltage into current. So therefore the current P divided by V. So the power is P is power 2 into 10 power 6 and divide by V. V is 10 kilowatt. Kilo means 10 power 3. 2 divided by 10 into 10 power 3. So here 10 power 3 go to this side, 10 power minus. So what will come? 10 power 6, 10 power minus 3, 10 power 3 it will come. Therefore 2 divided by 10. What will come? Yes. 0.2 into 10 power 3. 3 decimal point come to this side. You will get 200. So the current is 200 ampere. The power loss is equal to heat produced. So what is the power loss? Square value of the current and the resistance. So we have current, therefore 200 square into 40. What will come? 1.6 into 10 power 6 watts. Power is measured by watts, therefore 1.6 into 10 power 6 watts. Okay, right. And percentage of power loss, how to calculate the percentage? It's very simple. Yes, power loss, right, divide by given power into 100 percentage. So what is the power loss? 1.6 into 10 power 6. What is the given power? Input power 2 into 10 power 6, that is 2 megawatts into 100 percentage. So I can get 10 power minus 6 cancel, therefore 1.6 divided by 2, 0.8 into 100 percentage, therefore the power loss is 80 percentage. Which percentage? 80 percentage. Okay students, right. And case 2, the same power is given 2 megawatt and the resistance is 40 ohm and the voltage is 100 kilovolt. Therefore the same method I am taking. P is equal to V into I, therefore I is equal to P divided by V. P is 2 into 10 power plus 6 and divided by 100 into 10 power 3. Yes, therefore 2 divided by is 100. What will come? And this 10 power 3 go to this side, 10 power minus 3, therefore 10 power 6 into 10 power minus 3, 10 power 3 it will come, therefore 2 divided by 100 I can get 20 ampere. 20 ampere. Now come to the power loss. What is the power loss? I square R, 20 square into 40, therefore I can get 0.016 into 10 power 6 watts. 1 power 10 power 6 watts, therefore the power loss same one is power loss divided by the given power then to 100 percentage, therefore 10 power 6 cancel, therefore 0.1216 divided by 2 I can get 0.008 into 10 power 8 percentage, therefore I can get the power loss is 0.8 percentage. See this previous case, 80 percentage, 8 percentage. Okay, so what is the conclusion for this illustration? Yes, when we are increase the voltage, the power loss will be reduced. The power loss will be what? Reduced. Okay students, do you understand? Right. So based on this one example problem 4.16, right? Okay, see the example problem. An ideal transformer has 460 and is 40,000 turns in primary and secondary coil. So this is for primary and this for secondary coil. Find the voltage developed per turns of secondary coil if the transformer is connected to 30 voltage AC. So the voltage is 230, right? Okay. The secondary is given to the load resistance 10 power 4 ohm. So we have to calculate the power delivered in the load to the load. So we have to calculate power delivered. Okay students, yes, how to calculate? It is easy. So from the question, number of turns in primary 460, number of turns in secondary 40,000, and the primary voltage is 230, and the resistance is 10 power 4 ohm. So from that transformer question, please remember Vs divided by Vp, that is equal to Ns divided by Np. Please remember the equation. Vs divided by Vp, voltage in secondary coil and to the primary coil. Vs divided by Vp is equal to Ns by Np. So from that I am taking secondary voltage Vs. The Vp go to this side. Therefore Vs is equal to Vp into Ns divided by Np. I have all the values, therefore substitute the values. 230 into 40,000 divided by 460. So I can get 20,000 voltage. The secondary voltage is 20,000 voltage. So therefore the secondary voltage per turn, how to calculate? It is very simple. Vs, voltage per turns. How turns? Number of turns in secondary coil 40,000, and the voltage is 20,000. Therefore the secondary voltage per turn for single turn 0.5 volt. 0.5 volt. Okay students, therefore come to the power deliver formula. What is the power? V into I, because we have to find out in secondary coil, therefore Vs into Is. Okay, right, and Vs we have, and if I am taking I is equal to V by R. According to Ohm's law, I is equal to V by R. If I am taking that, yes, Is is equal to Vs by Rs. Therefore, in that V divided by R formula, substituting in this equation, I can get, see this Vs already there. Instead of Is, Vs by Rs. Therefore, Vs into Vs, Vs square divided by Rs. Okay, using Ohm's law. Right. So what is Vs value? 20,000. Therefore 20,000 square divided by Rs, resistance 10 power 4. Therefore I can get 40 kilowatt. 40 kilowatts. This is power delivered by the secondary coil. Okay students, right? Do you understand? Right. Next problem, 4.17. See this 4.17. An inverter is common electrical device which we use in our homes. When there is no power in our house, inverter gives AC power to run few electronic appliances like fan or light. An inverter has inbuilt step-up transformer which converts 12 voltage to 240 voltage. So 12 voltage to 240 voltage. And the primary coil has 100 turns, and the inverter delivers 50 milliampere to the external circuit. That is, output is 50 milliampere. Find the number of turns in the secondary and the primary current. Find the number of turns in secondary coil and the primary current. Okay students, in the inverter. Right. Now come to the solution. So from the given data, from the question given data as voltage in primary 12 voltage, secondary 240 voltage, the current in secondary coil 50 milliampere, because the output is from the secondary coil, therefore 50 milliampere. The number of turns in primary 100 turns. Therefore from the transformer question, I said no, Vs divided by Vp is equal to Ns divided by Np is equal to Ip divided by Is. The current ratio of primary coil to the secondary coil is K. Transformer ratio. From the transformer question, please check the transformer question. From the transformer question, I take this K is equal to ratio of current. So the primary current is what? Or Bs value is given 240 and Vp value is primary voltage is 12, therefore can get 20. The number of turns in the secondary coil, how to calculate? It is very easy. From this one, Ns divided by Np is equal to K. You have to calculate the secondary coil, therefore Ns equal to Np into K, because Np is given. So what is Np? 100 into K 20, therefore 2000. The number of turns in secondary coil is 2000. It is easy now. Now come to the primary current. How to calculate the primary current? From this side, Ip divided by Is equal to K. From this one you should take Ip is equal to K into Is, because this go to this side Is, right? Because I is given 50 milliampere, so therefore Ip is equal to K into Is. What is K? 20 into 50 milliampere. Is is 50 milliampere, therefore 20 into 50 milliampere is 1 ampere. Milli means 10 power minus 3, so therefore we'll convert into this single 1 ampere. So therefore primary current is 1 ampere. The number of turns is secondary coil is 2000. Okay students, it is easy now, right? It's very simple question. Okay students, do you understand? Right. So transformer topic is over. Based on the transformer, loss is over. So based on the losses and the power losses, 2 problems is over. Okay students, right? Students, up to this 1/2, yes, 1/2 of the lesson is over, and remaining half is alternating current. Okay students, so after this 1/2 of the 4th lesson is over. Okay students, yes, therefore you have to, yes, go through all the topics. Okay students, so from the power losses definitely 1 marks, and 2 marks problems will come. Okay students, right? Okay, right. Thank you students, we'll see you on next video. Thank you.